Welcome to this exciting journey into the world of differential geometry, the branch of mathematics that blends the elegance of geometry with the power of calculus to study the shapes, curves, and surfaces. This complete course on differential geometry is a step-by-step journey into one of the most fascinating branches of mathematics. From understanding the simplest curves to diving into the geometry of higher dimensional spaces, this course will guide you through the very essential topics in differential geometry. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the first lesson in learning differential geometry. Well, before we go into the curves and surfaces and twists and turns, let us first understand that what is a differential geometry. If I go by the definition, then it is very simple. It is a branch of mathematics that deals with smooth shapes, smooth spaces, otherwise known as smooth manifolds. Now, each of these terms, smooth and smooth spaces and manifolds, have a different meaning. Then you can ask me that something which is not smooth, that means rough or something like that, will it not be dealt into differential geometry? We will answer the question later. But first of all, let us see that the word differential geometry comprises of the first word, which is differential, which means using calculus and using differential and integral. And in order to study surfaces and manifolds, obviously these are local, not global in nature. The question is that what is the mathematics branch which deals with global curvature or global nature of these surfaces? That is called topology, which is out of the scope of today's video. However, differential means that we are using calculus to understand shapes and sizes, which are something very local. Going to the next phase, which is called geometry. Obviously, these have geometric properties, and we start with Euclidean, then we move into non-Euclidean, studies the different shapes and sizes. So here is a quick summary that a differential geometry comprising of two words is actually reflecting the core idea of using differential calculus in order to study and analyze different types of shapes and sizes which are smooth and which have got different types of twists and turns. From here we get a better understanding of the subject. So differential actually means that we are using something which is to differentiate or to understand the infinitesimal differences which are differential distances, concepts like that, using calculus. And when we talk of geometry, then the surface will have where all the physics or all the things which are twisting and turning taking place. And using calculus means that we are not using here a flat space, we are doing with some twists and turns and shapes and sizes. So the underlying structure of the entire physics or the mathematics depends on this, which is geometry. Now, differential geometry is called so. Why? Because it's a branch of mathematics that study the geometric properties in understanding using local differential calculus. So here we understand these things which we will essentially take up in the due course of time of this entire series: derivatives, local analysis, connections, and water tangent spaces. Now we understand that geometry is required because we take into account shapes and sizes and curves. But question is that why do we need to use calculus? Why calculus? Why not anything other than mathematics? Let us understand why you need calculus to understand differential geometry into this part of the video. Now, if I show you certain figures, for example, calculus, particularly differential calculus, uses this type of objects which are, have got shapes, curvature, lengths in order to calculate this. So we need a calculus. So applying the rules of calculus on what is called a manifold, although manifold has got a very technical definition, we will take it up later, but this is where we need the calculus. Also, in order to find the derivatives, finding slopes, we need them. Integrals, finding the area and volumes, how these things changes. We will see differential area, differential volume, how these things happen. And calculus also helps to analyze the properties of curves such as curvature, torsion, and arc length together. We will also see, which is a very important concept, calculating geodesics, which are the straightest possible path a particle travels in a curved space, and something which is called a tangent plane, just kisses the boundary, kisses the surface, which is called the tangent plane, where all the planes are tangent. So all of this requires calculus. As you can see, small infinitesimal changes, distances, integral volume, particle moving along in geodesics, these are required. Now, if I take this kind of a diagram where you see these lines are converging, it means a positive curvature. These lines neither converge nor diverges, it remains straight, so it is a zero curvature. And here the lines are diverging, so it is a negative curvature. So all these things are basically required to do calculus. So each of this object, the hyperboloid, the cylinder and the sphere, you can see they have small boxes, and these boxes are where we are dividing into infinite small distances. So if I zoom out one of these curved surfaces and I start differentiating this into small boxes, we get something like a differential area, which is calculated by dy by dx. So we are applying the rules of calculus on this type of a manifold, a hyperboloid, a sphere and a cylinder, in order to calculate that. Also, what an important point comes up is that all these things, you can see these yellow boxes, they should look equally, I would say, locally Euclidean, and when you zoom in and zoom, it becomes locally Euclidean. But remember, these are not Euclidean spaces, these are curved spaces. But manifold, the definition itself says that a manifold is a surface which should look like a locally Euclidean. We will take up Euclidean surfaces or Euclidean part manifold later, but this is how what justifies the need of calculus. So we need something which we call smoothness, because it is a function, is a property measured by continuous derivatives, and continuous derivative means that the function is differentiable and its derivative is a continuous function. So if f is differentiable, then f prime we call it as continuous. So this is a differentiable function. This is again and this is not a continuous. As you can see, there is a break. So if I take this kind of a shape and I try to make small boxes, that means I'm continuously differentiating them. We call it as a differentiable structure, a structure which can be divided. This is a differentiable structure, but this part of the surface, as you can see, this is smooth, so it is called a continuous derivative. So this actually justifies our question that why we need calculus. These are the reasons we need calculus. Now we come to a fundamental question through which we make the first baby step in the world of differential geometry is, what is a curve? Now, if I ask you a question that what is a curve, you might say that you can give a simple example. For example, you might give a straight line, y minus 2x equals to 1, although it is not curved. Or you can say it can be a kind of a parabola, or it can be a circle. So all these curves, as you can see, actually can be described by means of a Cartesian equation, which is this. And this equation is very important. This is the first step and requires a detailed understanding for learning differential geometry. So as we see that all these curves are described by this Cartesian equation, f of x comma y equals to c. So here what we are trying to say, this is again this equation, let me first tell you, it's a very generic way of representing curves in the Cartesian plane. So in each of these three cases, as you can see here, I would say the straight line, the parabola and the circle, this format is maintained by expressing the equation into as a function f of x comma y, where we will see now further what it is. So here what happens is that the equation defines the relationship between x and y coordinates. And for example, we can take a straight line. So if f of x ax plus by plus d equals to 0, here you will see that f of x comma y is equal to ax plus by plus d, and c is basically 0, that is a constant. So if we take the straight line, for example, this as an example, then from here what we can see, we get a graph like this. and f of x. So f of x comma y, which you are talking about, comes over here, and this is x plus y equals to 3, and c is equals to constant. So what does it mean actually? This means that the straight line consists of all points x comma y, where x plus y minus 3 equal to 0 is actually maintained in the format. So x plus y minus 3 equal to 0 is being maintained. Going to the next example, which is a parabola. The equation of a parabola typically is a quadratic equation, and it takes this kind of a shape. So here again we can say that f of x comma y equals to y minus ax square minus bx minus c, and again c equals to 0. So this f of x y, which we started telling that this is a very important equation. So this, for example, if we take f y equal to x squared, it would give this is a kind of just an understanding of how the parabola looks like. So f of x comma y would be equal to y minus x squared, and c again would be 0. From this equation, what we can understand is this means that the parabola is a set of all points x comma y, where y minus x square equal to 0 again maintains or preserves the format f of x comma y equals to c. And if a parabola, which I have not mentioned over here, shifts, for instance, y minus x square equals to 1, it could be written in a different kind of an equation. The third example is that of a circle. So the equation of a circle is something like this. And here again f of x comma y can be written as this. So I have taken the explicit and the implicit, which I am going to explain later. So it can be written as this, and again c equals to 0. So if I take an example of this, it would plot a kind of a circle like this with a radius of 2, and here again f of x comma y equal to x squared plus y squared, c equals to 2, and this means that again the equation is still in the form f of x y equals to c, and where the constant c determines actually the radius of the circle. So whatever be the circle, it goes ahead. So from these three equations, which we have just seen, that of a parabola, and before that we have seen a straight line, a parabola and a circle, we can actually now tell that if I take this equation, the general observation is that the function f of x comma y actually encodes, or it holds the entire shape of the geometric structure of whatever the curve that we are watching. If we take c, the constant, this may vary. It would represent a slope-intercept conditions, the focus of the parabola, or the radius of the circle, whatever it happens. So this format works very well because it generalizes the way we describe a locus of points in the planes algebraically, and the curve is a simple collection of these points. Now you might have a question, which is this: is there any other geometric shapes and curves which actually can be expressed in this general format? And the answer is a big yes. For example, if you take an ellipse. So the ellipse equation is something like this. Here again f of x comma y can be written as this, and we have taken c equals to 1. So from here what we can see again is a hyperbola. So from this equation, let me tell you that in the ellipse, what it says is that the set of all points x comma y, where the sum of the distances from the two foci is constant. That is why f of x comma y equals to c is clearly maintained. If you take an hyperbola, the equation looks something like this. Right, x minus f of x. Yeah, so from here again we can write the equation as this one: x minus h square by a square, and so on, y minus square, this one. And here again what we can say is that we can get into another, also what we can say that this describes all the set of points where the difference of the distances from the two is fixed, and again the equation maintains f of x comma y equals to c. We can also see exponential curves, which again takes this kind of a shape, and here what happens is f of x comma y equal to y equals to a e to the power kx. So there can be certain other equations like logarithmic, conic sections, level curves of multivariable functions, and so on. So yes, with this equation we can express other curves. Now the big question is that f of x comma y equals to c, we are constantly dealing with this equation, but what is the name of this equation? What is this equation called? Now that is what we are going to deal in the next part of the video. This is what is called an implicit function, a very important concept for understanding differential geometry. Now, if I take by the definition, basically an implicit function is one where the relation between x and y is given indirectly, often in a single equation where we do not take out y. So here is the definition. Often in a single equation where y is not explicitly solved in terms of x. Let us see one example. For example, if I take this one, which you can understand as a circle, here you can see the equation represents a circle with radius 1 centered at the origin, and y is isolated. Whereas if I take this kind of an equation, ellipse, for example, x square and so on, I'm not repeating. Here this equation represents, again, y is not explicitly I would say written. So this is how it is. Now if I now take an explicit equation, which is the opposite of implicit, the equation would look something like this. So let me tell you, an explicit equation is one where y or any other variable a, b, c, d, whatever it is directly expressed as a function of x. You can compute y explicitly at any given x. So this is called an explicit equation. Starting with the same circle, in the explicit form, we can take out this y we are computing now, plus minus y square root of y minus x square. So this represents actually the upper and the lower semicircles if it is plotted. And if you take the hyperbole ellipse equation, for example, then again what we can do is that we can calculate y. So this is the explicit form, or where it is the ellipses upper and the lower halves are being expressed. So this is what is called the explicit and implicit, and what we are doing is that we are actually showing you the implicit function. Now this implicit function, which we denote in differential geometry as we deal with more complexities, can be represented as this. This is what is called a set notation. So this describes a set of all points x, y in the two-dimensional plane that satisfy the condition of f of x equals to c, y equals to c. So it actually defines a curve in the plane R2. And this is a kind of a set notation. Let me explain you what are the components of that so that you get a better understanding. So this part of the equation means that the points x, y lies in a two-dimensional space that means real numbers in both x and y. If I take this part of the equation, it means that this is a kind of a condition. You can say it is a constraint or condition that the points must satisfy to belong to the set. And c obviously is the constant. So here, as you can see, is a constant. So the function f of x, y is a scalar function of two variables, often representing something. It can be a height or a distance or any other property. And c is a constant, and we are looking for all points of x, y where the function f of x, y has the value of c. Now, if I want to express this set notation, which is a very convenient way in using proofs in differential geometry, what we can do is that we can take an example of a circle, which is this one, and this represents the same kind of equation. So it shows that this represents a circle of radius 1 centered at the origin. We can take an example of an ellipse. Similarly, this represents an ellipse with a semi-major axis A and the semi-minor axis as B. And an example of an hyperbola would show something like this, and this actually shows an hyperbola. Now we come back to the original equation which we started learning, and I will explain you the parts. So first one is the C. You can imagine it to be a container, a kind of a holder where all the points that satisfy the given equation. If I take this part, it indicates that we are dealing with ordered pair of numbers, and each pair represents a point in a two-dimensional space. This one actually shows that it's pairs with x, y belonging to the set of all numbers. And this is, as I told you, this horizontal bar, the vertical bar is actually something which is given. It introduces a condition such that given that or so, and this part of the equation says that for a point x, y to be in the set C, the function f evaluated at that point must be equal to a specific value or a constant, which is c. So we will use this set notation often and on again in different areas of differential geometry, but this is just to give you an idea the components so that we can plug in the other values in due course of time and you won't face any problem. So this describes a curve as a level set of the function f of x, y. What is a level set? That requires an understanding. We will come to that later. Now, the biggest question is that we all understand implicit, explicit set notation, but what is the use? I mean to say, if you're learning differential geometry, why we are doing this? Now, there are several usage. Among them, the first part is that it actually helps to describe certain closed curves. Now, there are open and closed curves. We will deal with that later. And multi-valued relationships. It is also significant because it is very compact. You don't really need to write a lot, and the equation is closely tied. So we will see when we will deal with level maps how the geographical contour maps, etc., are being described with those. It is also used in geometry because it is used to define curves and regions and allows compact representation of conics, polygons and other shapes. Calculus, obviously partial derivatives. Implicit differential is used to find the slopes, and in physics to field lines and equipotential surfaces. These are used to represent using the implicit equation. So all of these are very, very important. Now, apart from that, something also comes up very important as we turn the pages, is that it gives you an intuitive grasp of geometrical objects, obviously, because in order to study the curves and surfaces, you have to learn all those derivatives, etc. You can also learn how to, which we'll do in the next video, that how implicit function can be written parametrically. It will help you to understand a transition in studying in higher dimensional analogs such as this one. And most importantly, the equation, this nabla f of x comma y, it is basically a gradient and it shows is perpendicular to the curve. And implicit differentiation also helps in to allow you to compute tangent. As you can see, this is tangent and normals are very foundational in differential geometry, as they generalize the tangent spaces and normal spaces in higher dimensions, and that we will see how we move up. So this is the reason, very important, we really understand implicit equation. They are very simple, intuitive shapes. They give you a complete understanding and they provide a foundation of studying hard dimensional objects. And historically, it connects the classical geometry with modern applications. Now, in the last part of our video, we are also now going to see that from the R2, that is two-dimensional, once we move into three-dimensional surfaces, how things happen and how things look like. Now, all these equations, these are examples of curves in the plane of R2. But what about R3? Now, in the axis, when we talk of the x-axis in R3 is basically given a straight line where y equals to 0. It means no displacement along the y direction, and z equals to 0, which says no displacement along the z direction. So that is what I have written, that this means that y coordinate of any axis must be 0 and z coordinates also might be 0. So if we plot this kind of a value, what we see is that this can go up to minus infinity to plus infinity. X can take any value, and this will also, the point lies entirely on the plane, and what will happen, this will also have a y and a z axis, obviously. So where y equals to 0 and z equals to 0, resulting in a straight line along the y axis. And so y equals to 0 and z equals to 0. So, and as an example in R3 defined by a pair of equations would be this one and this one. So these two are examples of R3, how it is dealt with this equation. Now, obviously, you might have a question that what are the examples of a curve in R3? Well, there are many, but just to tell you, first one is very interesting, which is called a helix. A helix is a very common curve in R3 and can be defined by this equation. So this part is the cylinder of radius r, and this is the linear relation between z and angle theta. So the first equation defines a cylindrical surface around z axis, and the second equation, z equals to theta equals to 0. This adds a linear variation of z with respect to the angular position in the xy plane, giving the helix. And the intersection of these two is called a helix. Second one is called a circle in a plane. Now, circle in a plane lying in the xy plane can be defined by this. And this is again the first equation tells is a circle of radius of r, and this is where plane equal to 0. So this would be that the first equation, x squared plus y squared equal to r squared, defines a circular cylinder extending infinitely along the z axis. Second equation, z equals to 0, restricts the curve lie to the xy plane, and the intersection is a circle of radius r in the xy plane. So we will pause in today's video there because something we are about to explain which will require a fresh new understanding, which is called a level curve and a level surface, and that we are going to cover up in the next part of the video. So thank you very much for those who have taken up time to watch this video. Please do subscribe to my channel Physics for Students and click on the bell icon to get all the notification from Physics for Students. You can write me and I always respond to this email ID. You can subscribe to my other channel exclusive to Einstein General Theory of Relativity, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students have just started this new video on a course in differential geometry. Please do let me know how do you like it and how things are going, and I will be soon back with more videos, but till then, goodbye.